Hi class, welcome back to lecture. So this is the last segment on our discussion of exoplanets. So the discussion today is a little bit of a downer. We're going to talk about planetary catastrophes because we've been talking about the conditions for planets which would enable life, but it's certainly the case that sometimes the conditions that are certainly prime and useful for life ultimately are removed or destroyed. And so we need to talk about that a little bit just so that we can understand what we should be thinking about the planetary population that we detect out there. But also, we're going to start talking about the search for extraterrestrial intelligence, which means we're going to return to the Drake equation. And as you may recall, a big piece of the Drake equation is how long a civilization might last, which can be intimately related to the conditions on the planet. So we got to talk about planetary catastrophes. I'm sorry, but it'll be probably the only downer lecture we have this quarter, okay? Okay, so in the background is a picture of the Chicago shoreline. This is a thunderstorm front moving out over the lake. So this is called a shelf cloud or a roll cloud, depending on the exact structure it has up here on the front. And I show this because for most of us, we've never encountered a catastrophe more serious than a major storm. Some of us have had the unfortunate experience of living through hurricanes or floods or maybe volcanoes, but for most of us, thunderstorms, hailstorms, blizzards are the sorts of things that we've encountered at the level of catastrophes. When we talk about catastrophe for today, we're talking about things that literally can completely wipe out the biosphere of a planet, because we're talking about things that very completely destroy the conditions for all life on the planet. Okay? Okay. So let me go ahead and start some slides, and we will talk about some things here. Okay, so planetary catastrophes come in many different forms. The kind of global unifying feature that we're interested in right here is that they influence the complete biosphere of the planet. And so those catastrophes can come from many origins. They can come from outside influences, things that aren't the planet itself. I'll call those existential threats or existential threats. It can come because there are things that absolutely without fail are going to happen to a planet no matter what. We'll call those inevitable threats. And then the last thing, I'm going to call them rare but common threats. And the reason I call them rare but common threats is that if you and I were just hanging out, you know, making Chicago hot dogs around the barbecue some afternoon, and we were talking about them, we might think these threats are rare, but as we continue to expand our census of planets in the galaxy, we're beginning to discover maybe they're not as rare as we think they are. And so that is very interesting, perhaps disturbing, but perhaps telling about the history of the evolution of planetary systems. Okay? So, the universe evolves. That is absolutely true. Everything in the universe changes. It was born at some point in the past. It has a life through which it changes its properties, it evolves, it grows, and then in the end, ultimately, it perishes. And that's a story that's true for the universe itself. It's a story that's true for stars itself. It's a story that's true for planets themselves. And the synchronicity of that idea with our perception of life is what makes defining life so hard. We haven't talked about that a lot since the very beginning of the course, but the fact is we can't easily describe what we mean by life, because if you just think about these kind of cycles of creation, existence, and then destruction, that looks a lot like the way you and I think about our own lives or our pets' lives or the life of a plant, right? And so this is one of the things that's hard, but it's that same synchronicity, that idea that the universe grows and evolves through phases, just like you and I grow and evolve through phases over the course of our life, that inspires kind of deep philosophical musings. It's one of those things that I think enthralls us when we talk about the stars and we talk about the universe and where it came from. That kind of parallelism with our own perception of our own existence, I think, is one of the things that makes us feel very deeply connected. And that's fine, because in fact, we are deeply connected. We are part of the universe. We are a representation of the universe trying to understand itself, which is what this whole story that you and I have been talking about this whole quarter is all about. Okay? So let's talk about the different modes by which a planet could destroy itself, by which a planet's life could end. So the first modes are the most depressing, okay? And those are what I call the self-termination modes. So these are ones that I think many of us are painfully aware of right now, because we, as the apex species on the planet at the moment, are largely responsible for them. So we live in an era that geologists currently call the Anthropocene. The Anthropocene is an era whereby if you look at the geologic structure of the planet, you can see the signature of humans in the geologic structure of the planet. And if we were to come back to the planet a million years from now and dig up rocks from this era, we would see things from us recorded in the rock. And that ranges from our transformation of the planet's surface to the transformation of materials into our the materials of our world, you know, metals, plastics, those sorts of things that won't decay for millions of years, and then the chemical shifts that we're creating in the biosphere of the planet as well. And so there are many things that we can point to that are kind of existential threats to the biosphere of Earth, ranging from climate change, which I think most of us are aware is the most serious challenge our civilization faces right now, and certainly one that we have some control over if we have the willpower to have control over it. There's something going on right now called the sixth extinction. We've talked a little bit about that. We are seeing a tremendous die-off in the number of species on the planet. That seems to be linked to the growth of the industrial era here on planet Earth. And then an existential threat that certainly was very prominent when I was growing up, when I was in elementary school, was the threat of thermonuclear war. And that has kind of taken a back seat, certainly in many people's minds, to some of these other threats that are facing our planet. But as many of you who follow the news know, this is still certainly an issue. There are still thousands of nuclear warheads on this planet, and the kind of childish behavior of governments, if I were to put a word, an adjective on their behavior, means that many of the agreements that have been put in place precisely to protect us from thermonuclear war, we seem to be backing away from. And that certainly is a cause of great alarm for many of us who lived through the Cold War, and this was certainly a big threat. I will point out that self-termination events have happened on the Earth before, and we've talked about that a little bit in the past. So you remember when the cyanobacteria became very prominent, they are photosynthetic, and so they had this gigantic moment where they spread across the planet and they were consuming the Earth's early atmosphere, which was primarily CO2. And the byproduct of that consumption was O2, oxygen. And so you'll recall that when we were talking about that transformation of the Earth's atmosphere, it made it very difficult for anaerobic life forms which can't thrive in an oxygen-rich environment, to survive. And so that was an example of the life form that was dominant at that time, completely changing the face of the planet. Now, that was billions of years ago, and life came on the scene. There was still some life left, and it evolved and it adapted to that. And so it is unclear that if you and I and our progeny fail in controlling our influence on this planet, whether or not some life may survive and evolve to fill whatever the new planet looks like. Okay? Okay, so this is self-termination. It's one that I think is very serious, but of all the ones that we're talking about, it's the only one that we have any control over, okay? Well, that may not be true, because this one is asteroid impacts. And as we all know, as long as Bruce Willis is still alive, maybe he'll be able to save us from asteroids, right? Right, okay. And if you have no idea what I'm talking about, go watch Armageddon. It's a great movie. Okay, so asteroids hit the Earth all the time. If you've ever laid out while you're camping and watched the night sky, you will see periodically a shooting star, as we call it, which is a typically a small fleck of dust, something the size of a pebble or a sand grain, coming into the Earth's atmosphere, superheating, getting very bright, and disintegrating. The Earth, on a regular basis, passes through the old orbits of comets, where the dust from a comet's tail has been left behind, and that produces the annual meteor showers that you get to hear about and may have gone out and looked at. Okay, so small stuff hits the Earth all the time. Something like 20 megatons of material per day falls on the Earth in the form of space dust. But periodically, and not infrequently, larger things hit the Earth. And as we've kind of touched on many times this quarter, smaller stuff hits the Earth a lot because there's a lot of small stuff. Bigger stuff hits the Earth less frequently because there's less big stuff left out there. Okay, but there are still things out there that are quite large. And so one of the things that we worry a lot about is that an enormous asteroid could hit the Earth and cause a global catastrophe. Okay, so the asteroid that hit the Earth and killed the dinosaurs was kind of kilometer-ish in scale, and it hit off the Yucatan Peninsula and wiped out enormous amounts of life on the Earth at the Cretaceous boundary in the geologic record. And we talked about that a couple weeks ago. So anything larger than about a kilometer would produce a global catastrophe that would destroy all life on Earth. These sorts of events kind of happen every 100,000, 500,000, million-ish years. And the longer we go, the more certain it becomes. So we think it's unlikely this is going to happen in the next decade. We think it's unlikely it's going to happen in the next millennium. But someday, it is absolutely assured that the Earth will collide with one of these floating bits of space junk still here in the solar system. And there are still plenty of them that are large enough that it could wipe out all life on the planet. That we think is in our distant future, but on the off chance that it's not, we are spending as much effort as we can looking for these things. We don't spend nearly enough money looking for these things, so we haven't looked at as much of the sky as we can or should, but we have found very many of them. And you periodically hear in the news, oh, this asteroid's coming within, between the Earth and the Moon in its orbit. And that's because we have expended some effort trying to locate all the big asteroids that cross the Earth's orbit. And I forgot to put it in the slides, but I have a picture from JPL, I'll put it in the slides that are online, that shows the orbits of all the known large asteroids of this size that cross the Earth's orbit. And so that's why we say it's not a question of if, it's just a question of when. Okay? Okay. There is a planetary catastrophe mode related to the atmosphere, okay? So a planet's early climate, early in its history, is never, doesn't necessarily have to be the same as what it is today. And we've seen this on Earth, we've seen this on Venus, and we've seen this on Mars. The early planetary atmospheres are not the planetaries that exist today because things have happened over the evolution of the planet to drive the evolution of the atmosphere into a very different state. And in all three cases, those changes in the atmosphere have been such that they have completely changed the character of the habitability of the planet. Okay, so in the case of Venus, it was largely geologic. We got the runaway greenhouse effect because we saw that the volcanoes dumped lots of carbon dioxide into Venus's atmosphere. That was enough to heat up the atmosphere, and it's a little bit closer to the sun to heat up the atmosphere, that it melted the water, which is also a greenhouse effect, which made it get even hotter. And as the water was slowly lost on Venus, then that prevented the carbon cycle from drawing all the carbon down into the minerals on the planet, and you get the runaway greenhouse effect. Okay, so we talked about that a couple of lectures ago. On Earth, there was the biologic conversion. Okay, so this is what we just talked about. The cyanobacteria ate up the CO2 and produced the oxygen atmosphere that we enjoy today. And then on Mars, I didn't put Mars here. Mars is just its physical character. You'll remember that Mars's gravity is light enough that it couldn't hold on to its atmosphere. And so over time, its atmosphere has bled off to space. The atmosphere is very thin today, and so liquid water can't survive on the surface. So on every planet that we've seen here in our solar system, its planetary atmosphere has changed dramatically. And those are things that are sometimes within the control of the life forms or caused by the life forms that live on it. But more often than not, if we say 2 out of 3 is more often than not, it's processes that the life forms have no influence on that actually drive the atmospheric conditions. Okay? Now, another big issue is stellar evolution. So stars, as we said when we started, they live their lives. And so just like when you and I are young, we were very different than we are right now in the middle of our life. And right now, if we look at the sun, if we look at any main sequence star, it's in the middle of its life. It's living its life, doing what it's supposed to do, getting up in the morning, going to work, turning hydrogen into helium. Next morning, it gets up, it goes to work, it turns hydrogen into helium. That's what stars do in the middle of their lives, okay? But as they get older, they change, okay? And so in particular, when the sun gets older, it's going to get a little bit brighter first. That's about 1 million years from now. A billion years from now. About 1 billion years from now, it will get a little bit brighter, and that will raise the temperature on Earth enough that the oceans are going to start evaporating away. And that's just like what we saw happen on Venus. Okay? As the sun ages, it's eventually going to become a red giant, and it will swell up. And as you can see in the lower graph here, you can see up here in the top graph, the habitable zone marked. It's been pretty stable for a long time. It's starting, we're just at that first start of it starting to turn and move farther out in the solar system. You and I certainly won't see the habitable zone change at all, but our descendants who live 2 billion years from now will see that the Earth is on the inner edge of the habitable zone. Okay, and so the Earth will sometime in the future become completely uninhabitable from the context that we think you need to be habitable. You have to have water, okay? But there's nothing that can be done about it because it's just going to be a consequence of the fact that the sun is moving on in its life. Okay, this happens to every star, and so stars eventually will destroy the habitability of the planets around them. Now, as the star dies, there's a couple of things that happen that continue to evolve the habitability. The first thing is that after it goes through this kind of slightly brightening warming phase that we were talking about, it's going to swell up to become a red giant. And if you go back and you look at the habitable zone plot I just showed you here, that big sharp curve, that post-main sequence habitable zone that's marked there, that's the so-called red giant phase when the sun's swollen up into this red giant phase that we see here. Stars, when they get very old, they puff up their atmospheres. They get to be enormous in size. The sun will swell up. Some of us estimate to the size of the Earth's orbit. There are estimates that suggest it might swell up to the size of Mars's orbit. There are red giants that are even larger than that, okay? But the point is they swell up and they will consume all the planets that are close to them. So Earth will, at some point in its life, be one of these roaster planets. It'll be very close to the surface of the star, and the star will completely roast it, okay? So if the star is big enough, about 8 times the mass of the sun, then after the red giant phase, its fate is to explode. So we call this a supernova explosion. And when a star goes supernova, that explosion almost certainly is going to destroy all the planets in the nearby parts of the solar system, okay? The amount of energy released in a supernova explosion is enormous. It is so bright that during the first week or month of the supernova's explosion, it can outshine all the stars in the galaxy. Okay, so there's 400 billion stars in the Milky Way galaxy, so that gives you a sense of how much energy is released in this explosion. It will destroy these nearby planets, and there will be rubble left. So that's the sort of stuff that collapsed again to form those pulsar planets that we talked about during the first half of lecture today. Okay, but the star itself, after it explodes, the core of the star collapses to form either a stellar skeleton, what we call the neutron star, We talked about those neutron stars in the first half of lecture today, or it collapses to form a black hole. Okay, so the planets, even if they were to survive this, but the rubble planets that certainly form afterwards around the pulsars, there is no parent star there to provide them with energy the way a main sequence star does when it's burning and providing light and heat in that way. It's debatable whether or not there is a quote-unquote habitable zone around something like a neutron star or a black hole. But I'm sure there are scientists out there who have thought about that, and I certainly haven't. But okay. So the last catastrophic event that I want to talk about is actually one that I like a lot. Okay, and I like it not because it's catastrophic, but because it tells us something very fundamental about the nature of the formation of planets in the galaxy. Okay, so the last catastrophic event is the permanent ejection of a planet from the solar system as it's forming. One of the things that we have seen happen when we simulate these things on computers is that the planets all form, and you'll remember one of the problems we have is getting big planets in close to the star to form those hot Jupiters that we see. And so one of the things that we see in our simulations is sometimes planets encounter each other. And when that happens, a planet can get a gravitational slingshot that will break it free of its star and send it out on its own into the galaxy. Okay, so that's what we call a rogue planet. It's a planet that's not tied to a parent star. Okay, so we've seen these things in simulations. We're like, wow, that's a neat idea. But as it turns out, we can actually find them out in the galaxy. So there are about 20 of them known already. We see them a lot in simulations, and in fact, we suspect there may be as many as 1 billion rogue planets floating around the Milky Way in order to account for the architecture of solar systems that we see. Okay, so this is a particularly famous one. It has a weird name down there, PSO J3118.5-22. This is about 6.5 times the mass of Jupiter. Okay. But it's floating alone, all by itself, out in interstellar space. It's big enough, it generates its own internal heat. So that's how we actually find these things. We can see them in infrared, and but it's floating around all by itself. And so we have lots of questions about these. Okay, so for instance, they're all pretty big, all the ones that we know of. So they're gas giants. Do they still have their moon systems with this? You could imagine if Saturn got ejected and took Titan with it. Titan's one of the places that we imagine looking for life. You can imagine if Jupiter got ejected and took Europa with it. Europa is one of the places we imagine looking for life. And that's particularly interesting because a place like Europa, the source of its energy isn't the sun. It's the gravitational influence of Jupiter tugging on it all the time. So if a rogue planet like this carried its lunar system with it, then maybe there's the opportunity for life to be there. We just don't know. Okay? So these are very exotic. We are slowly discovering them. As I said, there's about 20 known now, but we expect to discover many more. And in fact, we're beginning to think they are very common. Okay, and so this is what I had told you at the beginning, rare but common. If you and I had said, ha ha, wow, can you imagine a planet getting ejected? I've seen a cool science fiction movie about that, okay? When worlds collide, that's a great example of a movie like that. But indeed, it's starting to see as we get more data, as we become better observers, as we begin to understand the universe more, it seems to be the case that maybe that rare event is actually more common than we thought. And if it is more common than we thought, then that means it's probably more important than we thought in the whole story about how exoplanets form and how they come to be in their current states that we see them now. Okay? So that's all I'm going to say about exoplanets for the week. It is a long weekend now, so please enjoy yourselves. Next week, we'll start talking about interstellar travel, the Fermi paradox, extraterrestrial intelligence, and all of that good stuff. And that will take us to the end of the quarter. Okay? So I hope you're all doing well. Take care of yourselves, and I'll talk to you again soon.